Hello, everyone. This is Mouli Chowdhury. I'm your host for the evening, and I welcome you all to the Young Scholars Exposure event. This is the fourth event, uh, which is an initiative of the JBSPDF uh, forum that we have created. So, for people who have been here before, the format is, and who have not been here, let me introduce the format to you. So our speakers will be given 20 minutes each, where they'll give their talk or presentation, followed by a 5-minute question and answer round, where the audience can ask any questions that they want to, followed by a 20 minutes time period during which our esteemed reviewers will be giving us their opinion as to how our speakers fared during their presentation. So before I introduce our reviewers to you, our speakers to you, let me first tell you who our reviewers are for the evening today. First we have is Dr. Sulalit Bandyopadhyay. Dr. Bandyopadhyay has reviewed before as well. He's a JD scholar from the year 2006, and he's currently an associate professor within particle engineering and hydrometallurgy at NTNU. And he's also a researcher at the Department of Water Management, TU Delft, Netherlands. He earned his Ph.D. in chemical engineering, and he's currently a member of the operative group for the Gemini Center within hydrometallurgy, HYPROS. Our second reviewer of the evening is Dr. Sitabhra Sinha. Sir is reviewing. We are very happy to have you on the panel for the first time, Dr. Sinha. So Dr. Sinha is a JD scholar from the year 1989. He is a professor of theoretical physics and computational biology at the Institute of Mathematical Sciences, India. He received his bachelor's in physics from St. Xavier's College, Kolkata, his master's in pure physics from University College of Science, University of Calcutta, and his PhD from ISI, where he was affiliated with the Machine Intelligence Unit. So I welcome you all to today's event. Without any further ado, I will move on to our very first speaker, Mr. Sourim Banerjee. The talk of Sourim's, the title of Sourim's talk today is Origin of Void Formation Inside Solid-State Batteries Using Kinetic Monte Carlo Algorithm. And Sourim is a JD scholar from the year 2016. He has completed his B.Tech, M.Tech dual degree from the Chemical Engineering Department at IIT Kharagpur this very year. He will be joining the School of Mechanical Engineering at Purdue University under Professor Partha Mukherjee. He will be primarily working on computational modeling of electrochemical systems and solid-state batteries at Purdue. So, Sourim, whenever you're ready, you can start sharing the screen.
Yeah, thank you. Can you all see my slides and also can hear me?
Yes. You're perfectly audible and we can see the screen. Please continue.
Okay. Okay, thank you for the introduction. So I'm Sourim Banerjee. I'm JB Scholar of 2016, and I recently graduated this year from Chemical Engineering Department. And my topic of my topic for the talk is the mesoscale origin of void formation inside solid-state battery using kinetic Monte Carlo method. So let's get started. So the overview of my talk will consist of the brief introduction of the electrochemical cell, that is primarily the battery, and then we move on to the solid state battery and why we are talking about solid state battery in spite of the conventional lithium ion battery and so. And then the objective of my work and the presentation, and I briefly discuss about the kinetic Monte Carlo method after that, and again at last the results and also the takeaway message at the conclusion. So yeah, So, what do you think when you hear about a battery? So you hear about when you hear about a battery, you think of electric vehicle because that is the most uh, that is the most very topic we are now discussing on, or in a battery in a mobile cell, or in power bank, or any other electronic devices you have. So there is a lot of use of battery in our day-to-day life. So it's important to know about it, and continuously think how to improve them from its initial technology to many more other technology. And with this, when you think there is a lot of application of battery, and when you come to know about what is the science, what is inside of a battery, you may recall this image. So it is a image from it is an image you remember from your school days. It is a brief outline of a battery or electrochemical cell, where there are two current characters. One is positive and another is negative current characters. There are two electrodes, positive and negative electrode, and there is a separator in between them. So the most important work for the separator is to restrict the electrons to move inside of the cell. So the ions moves inside of the cells, and the electrons moves through the external circuit when there is a load or a resistance. So if we talk about discharge of a battery, then the oxidation happens in the negative current characters, and the reduction happens at the positive current characters, as we remember. So at that time, the positive ions move from anode to cathode, and the electrons moves at the external circuit in the same way. For charging, the movement of the ions and the electrons are exactly opposite, but the ions also move inside of the battery cell, and electrons moves in the external circuit. For negative ions, it is just opposite of the positive ions, the movement of the positive ions. So, what is the difference between a conventional electrochemical cell and a solid state battery? So we know about lithium ion battery. When in lithium ion battery, there is electrolyte solution of a there is a liquid electrolyte where there is a lithium salt solution inside of the cell. But for solid electrolyte, the liquid electrolyte is for solid state batteries. The liquid electrolyte is just replaced with the solid electrolytes. So structurally, there is no difference except the phase of the electrolyte is from liquid to solid. But there is some effect. So due to as the electrolyte is solid, so it is very less chances of flammability, and also high charge density due to available of free ions inside of them, and high ionic conductivity inside the solid. So the solid state battery seems to be very much useful, or very much usable than the conventional lithium ion batteries, but there are some problems. The first problem is the anode depletion. So during the discharge, the anode gets depleted in solid state batteries, and there are in during charging there is formation of filaments inside the solid electrolyte, which actually results into short circuiting. So at first we talk about the discharge and the anode depletion, and we move to the charging cycle later on. So during discharge, as I have mentioned earlier, the electron flows outside the outside the external circuit from anode to cathode, and the lithium ions move from anode to cathode inside of the cell. So now, if we zoom into this area, we get a interface between the solid electrolyte and the anode. At the interface, there are a lot of lithium atoms are there, and when there is electrochemical reaction, that means during discharge there is oxidation happening at the interface. The lithium ion get oxidized, forming a lithium atom gets oxidized to forming a lithium ions, and a electron inside the at the interface. So the electron is actually vacant because the the position is only occupied by electron, so we can call it as a vacancy. So now the when the discharging cycle is going on, during at some point there is a lot of formation of electrons inside the uh, atoms, which are also called as vacancies. And the lithium plus ions are formed at the solid state electrolyte. And there are three mechanisms which is going on simultaneously here. The first one is the electrochemical reaction, as I have mentioned, at the solid electrolyte interface. The second one is the ion transport at the solid electrolyte. So the lithium ions are getting transported or diffused to the solid electrolyte to reach to the cathode on the other side. And there are the transport of vacancies, or in the other words, you can say the transport of lithium atoms in the other way. So the vacancies are transported from the interface to the bulk, and these three mechanisms are happening at the same time. So the objective of my work and that this presentation is to model a kinetic Monte Carlo computational algorithm to find out the anode depletion issue and the filament formation issue. And at the end, I will talk about the critical current density for against external pressure. So there is a need of putting external pressure to increase the contact area, due to which I have to have a critical current density. There will be a limit that I will find in the end. So let's talk about the kinetic Monte Carlo algorithm. What is it? So it is a energy based optimization algorithm for a large population. So let's say you have a system which there is a lot of atoms or species are in the systems. So let's say it is at any in and at a equilibrium, and now there is some external disturbance to it, which causes the system to follow a dynamical evolution. So at the transient, the property of the system will change as a function of the space and time, and it will eventually come to a stable equilibrium. So the transient to stable equilibrium, this part can be find out by the KMC algorithm. And at the stable equilibrium, it is nothing but the energy minimized system state, which can be find using the kinetic Monte Carlo algorithm. But why we are using it? We using because this is a mesoscale system, so the length scale are not very small, neither it is very neither it is very big. So it is in between, close to the micrometer length scale. So we have to we the ideal model we can use, that is the KMC algorithm over some other algorithms such as molecular dynamics or density functional theory. So let's uh, let's give have some let's have some idea about how we are going to do in a computer, how to use this algorithm to get the final morphology. So let's say if this is the state of the system, and there are four species. The first one is the solid electrolyte molecule, the second one is the lithium ion, third one is the lithium atoms which is present in the anode, the fourth one is the vacancy or the electrons. So we give some numbers to them. Then we create a 2D array of them to substitute the actual molecule with a number. So here 2 is the lithium ion, one is the solid electrolyte molecule, and respectively 4 is the vacancy and 3 is the lithium atom. So we create this 2D array, which we name as lattice. And the typical length scale of for each of the lattice dimension is almost point half of the nanometer. So if we take a domain of 100 cross 100, so it is almost zero point 0.5 micrometer. So from this lattice array, let's say it is m cross n lattice array, Then we create another position matrix to map this atoms or this number to its positional numbers. So let's say, but we only take the species which are actually taking part in the physical mechanisms such as transport or reaction. So let's say these two, the two means the lithium ions is actually participating in the reaction. So we put the details here. So we put the x and y coordinate as well as the identity of the species. And there is 4. 4 is the vacancy which is also participating in the reaction. So 4 is also tabulated here. And the 3 is lithium atoms, but it is situated at the interface. So be this will be oxidized later. So there is information about that atom, but not any other atoms in the bulk. So they are not participating in the reaction. So now the KMC algorithm is actually, let's say this is the initial state of the system where I get the position matrix like this and find out the rate for each event. So each event means if there is transport of vacancy or the lithium ions, then we write down the corresponding transport rate, and if there are reaction happenings, then we put down the rate of the reaction here. Then we sum up all the information, all the rates, and gives the and sum them up and make the total rate is k total. So now as we sum all the rates and find out k total, we choose a random number and find out a number that is r. So if there is a cumulative sum of these values, R will situated in between any of the two consecutive slabs, and that's corresponding to that slab. The corresponding event will be executed. Let's say for pth number species, that will move up, down, left, right if it is a ions or a vacancies, but it will get oxidized when the interfacial atoms will be chosen. Then we update the array and again repeat itself as long as there is some equilibrated morphology we get. So the complete takeaway message is that we execute the KMC algorithm to reach to the final state from an initial state, and the vacancies at the beginning of the simulation, the some vacancies will be there. That is actually the disturbance to the KMC disturbance to the systems. So let's define some physical quantities. There is a Butler-Volmer equation called Butler-Volmer equation that gives us the reaction current densities, which is a function of temperature, and some other parameters, which is intrinsic parameters to the manufacturing materials. And then we calculated the reaction rate and also the diffusion rate for ions and for vacancies. So the reaction rate and the diffusion rates are all function of temperature. Then we define two dimensionless number. One is lambda, that is j by k naught, and one is k, that is k, the diffusion rate by k naught. K naught is a standard diffusion rate for vacancies in room temperature. So as we vary the value of lambda and k, there is two distinct regime we can see. So one regime is a diffusion dominant regime where k is much higher than lambda. In this case, there is a lot of the diffusion rate of the vacancies is much high. So the contact is remain the contact has not been reduced, and there is a stable contact area between the solid electrolyte and the anode. Compared to this, for unstable regime where the lambda is very much high compared to k, there is only the point of contacts and most of the anodes are getting void. So this is referred to the reaction dominant regime. Now let's plot the contact area values in a graph of having the x-axis as lambda and y-axis as k. So for k high k values, there is a 90% of contact area compared to for high lambda values, that is a 30% of contact area. And corresponding the dynamic evolution of contact area can be calculated using the discharge capacity. So with discharge capacity means number of electron gets get produced. So the contact area is very much decreasing rapidly for the unstable case, where there is very high reaction current than the diffusion rate. But for diffusion dominant regime, the contact area remains at the initial value. So for the from the discharging to the charging cycle, everything will be similar, but there is a current source at the external circuit, and the direction of transport of lithium ions and the electrons are in the opposite direction. So if we also zoom into this case, there is transport of lithium ion from the cathode to anode, and these are getting deposited at the interface where there is still the contact is remained. So there is formation of lithium ions which is penetrating inside the solid electrolyte. So there are some experimental evidence that we are talking about, that there are formation of filaments is there. So these are the scanning electron microscopic images for lithium deposited on a solid electrolyte of beta Li3PS4, and there are some filament tip is there, and due to some external pressure, the filament tips are already broken in some cases. So these are the some experimental results we know from the literature survey. So as one of my colleagues has solved the charging cycle dynamics inside the solid electrolyte. So there is a very electrochemical potential which actually indicate the filament formation. Also, if we consider the reaction current along with the interfacial direction, so there are some reaction spike for three values of the applied current. So this reaction spike actually indicates there are formation of filaments and point contacts through which a lot of current is flowing. So one of the remedy which typically people use is that to put external pressure to uh, increase the contact area. So if this is the initial state, then after discharge there are formation of vacancies, and if we put external pressure, so the vacancies get merged, and then there is increase of the contact area. This is one of the remedy which people choose. But there is some problem after the charging cycle. So after the charging cycle, there are formation of filaments. But if we now put pressure in the on the top of the battery, then the filament tip get broken, and there is a possibility of damaging of the battery. So now there is there is we calculated the contact area map from the discharging of the battery, and the critical stress, the maximum stress generation is a function of the over potential. The over potential actually proportional to the reaction current, and we can see that the critical applied current is 0.5 milliampere per centimeter square for a particular solid electrolyte, which is LLZO. So we can see this is the critical applied current which I have talked about earlier. So in conclusion, we can see so that the diffusion is the stabilizing mechanism here, reaction is the destabilizing mechanism, and the most important takeaway message is that the manipulated variables we can control. So temperature is one of the manipulated variable through which we can control the diffusion as well as the reaction rate, and another is the applied current. So after a critical applied current, we cannot exceed the applied current as to in order to not damaging the battery. So now we are going for future work with this. So for more refined diffusion mechanisms, as well as to build a 3D model of this. Thank you.
Thank you, Shori. Um, Thanks for that wonderful talk. We will quickly move on to the audience and ask if there are any questions. In case there are any, you can unmute yourself and ask that question to our speaker today. Okay, I don't think there are any questions. Then we can move on to our first reviewer, Dr. Bandyopadhyay. If you could please let us know what you think about today's
Thank you,
topic.
Sourim. Yes, you can hear me all right. And thank you for a very nice presentation. I have some few general comments and then maybe a bit more specific comments with regard to this presentation. So I think this was also a bit of or close related to what kind of work we do in my own research group, but more on the lithium-ion batteries. But we're aware of this SEI and challenges around that. It was also nice to hear the developments on the SSBs or solid-state batteries. So I'll first come down to some basic points, which is when you are preparing for such a presentation, which is more to a generalist audience than a specific audience, what I felt was missing was that you didn't give me the bigger picture of your work, meaning how what you are doing now is going to impact either the future of solid state batteries or what question are you exactly trying to answer. You are doing Kinetic Monte Carlo, which is a very nice approach, as you mentioned. You kind of convinced me that there is quite some work that you have done along with your colleagues, I guess. But I didn't get the main message of where is your work going to impact. And as a generalist audience, I would have loved to know that. Why are you doing what you are doing? So that was one point. The second more important point is that in connection to this point of not getting to know what you are intending to do in the bigger picture, you probably missed out what has already been done in your field of work. So I was not able, as a generalist, I was not able to achieve to a conclusion for myself if this is a work which has a huge significance or if this is a work which is primarily a little bit of pushing along the boundary where many people are already contributing. So I was not able to judge the originality or the novelty of the work. So in your, where you are now in your current academic career, it's very important that you cite references to other people's work and show what is missing in your field so that it's easy for the audience to capture, okay, this is where you are contributing. So other people's work needs to be kind of told. You mentioned that we have learned something back in school, but I'm pretty sure that you are not impacting that understanding through your work, but you're rather impacting a bit bigger cause. So the literature review, as we call it in classical Ph.D. literature, is that was missing, or at least one slide on that would have been great. And then what I felt was that since you didn't say what people have already done, you specifically didn't mention what people have also not done, where you are impacting again. So all these 3 points are connected to the fact that I couldn't appreciate how much of this work that you have done is very novel and how much of that is filling the gaps in the literature and how will it help society or the bigger picture. It could be a very theoretical work, but as I understood from being a specialist in a part of your field, that this will impact several decisions we take on switching between two kinds of batteries and the whole electrification debate around the world. So I think there you could have come in very nicely. So that was one major point. The second point which I had was primarily about all work that we do at this level of your research is not a single unitary contribution. in the field, I think so, because you have taken help and collaborated with other colleagues and probably your supervisor. I didn't find them anywhere. And it felt like it was a one-man story without any references, which I'm sure is not the case for such a nice piece of work. You also mentioned colleagues somewhere, but you didn't cite their work or, I mean, show them. Maybe in this after this thank you slide or before, there are different ways of referencing or referring back to your own research group that you're part of, or collaborators in other universities, but that I didn't find. So it felt like this was a one-man army working on a very, very complicated problem, which I hope is not the case. So those were the two main points, I would say. And then there were some minor presentation related skills, which I would like to say. So if I want to go back to a certain slide of yours, I found that your slide numbers are missing. So it's a bit difficult for me to, and also for you to navigate back if there is a question answer session after this. I would really like you to consider the choice of colors on your graphs, because you have used very consistently red, green, and blue, and several people in the world are colorblind. So please ensure that you use colors where people are able to distinguish, because if you are speaking to an audience with color blindness, probably they will only see two of your lines or one of your line. The others are blank to them. They can't distinguish it. So the use of right colors probably would be useful. And you use a lot of nice pictures from the internet, and I guess it's important that you cite the references again as a below those pictures or towards the end, doesn't matter. But I'm pretty sure that those pictures were not made by you, so that you can classify them as your pictures. So they have been taken somewhere from the internet, from other references. And throughout your presentation, there was only one particular reference that was mentioned, the 2017 paper towards the end. But other than that, it seemed like that there were spaces where you could have used the referencing system, because it accounts to a form of plagiarism in the bigger picture if proper citations are not made. Yeah, and then finally, something on the maybe one quick question about what could have clarified something. You did mention that you didn't want to go for DFT or other kinds of tools, primarily based on your mesoscale situation that you have in your problem. But it might have been nice to also give an introduction to the why kinetic MC is useful in that sense, where you briefly discuss, since we share the same chemical engineering background. So with the transport and diffusion process that you mentioned, it could have been nice to cite that a bit in a generalist term before you went into saying that these are two important processes which you are trying to distinguish, because that's almost all chemical processes have this to, the transport limitation and the diffusion limitation, the reaction and the diffusion limitation. So I was expecting something more general to kind of bring in other kinds of audience also into the core of your talk, which was, by the way, on transport and transport mechanisms in different capacities. And the last comment before I pass on to the next reviewer is that I followed, let's say, 75% of your presentation very nicely. When it comes to the last part, where you suddenly showed in a lot of new and interesting data, I think you could have skipped them for this presentation, because I think for a generalist audience, it was difficult to understand the implications of those figures, because you didn't explain those terms before. You suddenly brought those results. And there I felt that those slides were kind of taken from another presentation, which was a more scientific presentation, or this was also scientific, a more specialist presentation, and you decided to involve those slides. It kind of had a break of flow of the presentation after when you started talking about the charging part of your talk. But nonetheless, it was overall very interesting to listen to the work that you are doing, and I hope these are comments more that will help you make a better presentation. Thank you.
Thank you.
Thank you, Dr. Bandyopadhyay. Moving on to our second reviewer, Dr. Sinha. If you would please let us know your opinions about Sourim stock.
Hi, can you hear me?
Yes.
Yeah, you're perfect.
Okay.
Yeah.
All right. So first of all, Sourim, thank you so much for a wonderful talk. Uh, I was kind of a bit worried when I heard the title of the talk because I used to always consider battery to be one of the driest subjects on earth. Partly being the son of a metallurgist who used to work on battery development may have something to do with it, because when you're a teenage rebel, you think what your father works on is the worst thing possible in the world. I never actually, I deliberately chose to steer clear of anything having to do with batteries ever. Um, so it was great to actually listen to you, talk about batteries, and to know that, there's some really cool science associated with it. So Sulalit has already, outlined many ways you could improve your presentation even further. So I won't go into those points, except maybe emphasizing once more the point Sulalit made towards the end, that if you have used images from the internet or from other sources, it's very important that you always mention the source in your slide, because nowadays, all over the world, people are getting very serious about, plagiarism, and this can be seen as a kind of plagiarism. So please be, whenever you give such a talk on future occasions, please make sure that, you always give the source of any image that is not generated by you. Okay, now trying to go through the talk. So I made some notes about, like, if I was giving the talk, how would I have, tried to go about it? So, you can pick and choose this, because, everybody has their own style of giving talks. And I'm no way saying that my way of giving it is any better than the way you chose. It's just, like a different way of looking at, how the same story might have been told in a different way. So incidentally, by the way, I really like the way you started out by saying that, what do you think when you think of the word battery? Interestingly though, your examples aren't what occurred to me. So, you gave the example of car, mobile phone, power bank. When I hear the word battery, what I think of are, the torch and the radio, because, as a kid, that's what I grew up, being used to, like, these are the things that one uses batteries for. But I really appreciate the fact that you kind of try to connect it with some everyday experience. Then you went into the interesting picture where you showed what is inside a battery. Now, I was wondering if you could possibly think of animating this picture, because there is a way that you could make this graphic even more interesting by showing actually the movement of ions in that picture, which would, in some sense, attract the audience more. And if I was giving the talk, I would probably have started at this point with some historical story, like basically starting from the Leyden jar, maybe, how you put this two metals in a bath of acid or whatever, and you have essentially a primitive battery, and how we have come quite far from those days where instead of a liquid, we are now thinking of using a solid. So I really appreciate the fact that how you listed out the advantages and then also spoke about the issues. One minor point, maybe you could have thought of having a separate slide when you spoke about the issues, because they were given in a very crowded slide, and I might have missed the very important point that you were making, that there are in fact critical issues in using solid state batteries, namely that of anode depletion and filament formation. Again, the slide following that, you could have thought of using an animated figure rather than a static figure, which would have made it even more interesting when you started showing how, as you have lithium ions being transported, you leave behind voids, and how these voids essentially form these shapes. So could have tried to see if you could form some kind of animation where you gradually have these voids forming by more and more, circular shapes clustering together. Um, the point that you made about anode depletion, filament formation, you went through too quickly, and I really couldn't figure out why these were issues. You mentioned very briefly short circuiting in the context of filament formation, but I kind of was left wondering, how filament formation would lead to short circuiting. So maybe giving the audience, some link as to how these two connect might have been good. In a sense, the least satisfactory slide of the talk was the one in which you introduced Kinetic Monte Carlo, because you don't really explain what is Kinetic Monte Carlo. I mean, in a sense, you say why you use Monte Carlo. So, like this graphic you had where you connect initial state to transient to the stable equilibrium, and you have an arrow which is labeled with Kinetic Monte Carlo. It just says where you're using Kinetic Monte Carlo, but you never actually explain Kinetic Monte Carlo. Now, I mean, I do understand that time is a constraint, but, if you could have used the example, the very old example of, what exactly Monte Carlo involves. So for example, people often give this example that, suppose you're trying to calculate the value of pi. So what you could do is you could draw a circle and you could start throwing needle, and you ask how many times does the needle fall within the circle and how many outside it, and from there, just by looking at the ratio, you can try to estimate the value of pi. So in a sense, just by doing operation which is by nature random, is by nature stochastic, you could actually try to do a kind of a definite computation. So that would actually give a sense of how stochastic operations can nevertheless give rise to solutions, right? So that would have been good to introduce the audience to the entire concept of a Monte Carlo, because that may not be known to your entire audience, especially to a generalist audience like this. And also a point that Sulalit already mentioned, you had this point about that Kinetic Monte Carlo is appropriate for mesoscale and probabilistic system, but the question of a generalist audience is, so what? You very briefly mentioned molecular dynamics and density functional theory, but it's only people who have worked with molecular dynamics would know what exactly do you mean. The fact that molecular dynamics involves actually explicitly simulating each of these individual molecules or ions or whatever, and that's computationally extremely expensive. So it's a much more cheaper option if you can if you can get away without actually explicitly simulating them. But to an audience who has never done molecular dynamics, this point would be too opaque. So maybe you could either mention why is it more why is it useful to have Kinetic Monte Carlo over molecular dynamics, or you could maybe skip mentioning that, because otherwise you're leaving the audience somewhat mystified. Then you come to this question of then you come to the slide where you give details of the implementation. That's a very nice slide where you essentially show the mapping from the picture you had of this lithium ions moving across the interface, and how you map it onto a lattice, and then finally to a position matrix. That's a very nice slide. It makes it very clear what you're doing. But then again, when you move on to say that, look, this hash P will move randomly up, down, left, right, or it will get oxidized. Again, you moved so quickly, it wasn't quite clear to me how this connected with what went before that. Then the slide immediately following that, you had all these physical quantities like reaction current density, reaction rates, diffusion rates. You are very likely to lose an audience, with a slide that is so crowded and, where you just read through all these things without actually telling us how it's in some sense connected to your story. So, it just looked like lots of, different expressions. And then he moved on to this, stable and unstable regimes, where he's talked about a diffusion dominant regime and a reaction dominant regime. And you showed this contact area map where you had K and lambda on the two axes. But by this time, I had kind of lost touch with what is K and what is lambda. Since this is not a paper, I can't even refer back and ask, what does K and lambda mean? So you might want to give the audience a helping hand by just mentioning them to again what is K and lambda, or maybe just having them mentioned in that graph. And then you of course move to the charging cycle, and there were a few interesting slides like the reaction dominant regime where you showed how the reaction current distribution varies in position, but it was gone through so quickly that I couldn't really see how it connected with the rest of your story. And you had this remedy about putting external pressure, but you mentioned that a battery is damaged if the filament is broken, but it wasn't quite clear to me why that is the case. And then of course you moved on to the conclusion. The slide that you had on critical current was, of course, you went through so fast that I couldn't even get how it's connected to the story. Now, in the conclusion, you mentioned some very interesting points. You mentioned that the diffusion defines diffusion is a stabilizing mechanism, reaction is a destabilizing mechanism. Now, I'm wondering whether you are familiar with the reaction diffusion equations that were popularized by Alan Turing, which are in a sense the workhorse of physicists working on pattern formation. Now, we tend to use reaction diffusion equations in all sorts of different contexts, and we of course know that that reactions essentially give a nonlinearity to what is otherwise a very dull kind of equilibrating equilibrating system. So if you just have diffusion, it will just tend to equilibrate the system towards absence of patterns. But the moment you have reactions, that kind of introduces a nonlinearity which allows interesting patterns to form. So I'm wondering about the broader aspect of your work. Have you thought of connecting your work to this much more broader paradigm of reaction diffusion systems, which are known to essentially allow non-equilibrium pattern formation in physical systems across the spectrum, and not just physical systems, even biological systems exhibit this kind of reaction diffusion mechanism of pattern formation. So if you could think of how your specific work ties up with this more broader aspect of reaction diffusion mechanism based pattern formation, it can give a generalist audience something that they can take home with. That it's your work is interesting not only because it says something about the battery, but also can connect to, let's say, the systems that maybe members of the audience actually work with. But overall, I found your talk extremely nice, and please keep up the good work. Thank you.
Thank you, sir.
Thank you, Dr. Sinha. Yeah, thank you, Sourim, once again for that wonderful talk. Well done. So we'll move on to our second speaker today. Miss Bidisha Dey is our second speaker, and the title of her talk is Geochemical Signatures from the Earth's Mantle and How We Find Them. So Bidisha has completed her MSc in Geology from the President's University in the year 2016. She is a JB Scholar of the year 2011. Her topic of research in Masters was the ages and structural and metamorphic characters of Archean genesis of Deoli, Rajasthan. She worked in the Earth Science Department of IIT Bombay as a research scholar for a year before moving on to Hiroshima University in the Department of Earth and Planetary Systems Sciences as a PhD student in the year 2017. Her topic of research is isotopic geochemistry of Cenozoic basalts of East Asia. She has just defended her PhD thesis on this topic, and she is awaiting her date. Bidisha Dey, the floor is all yours. You can share your screen. Yeah.
I have shared my screen. Can you see it?
Yeah, it is visible. Yeah, please carry on.
Okay. Thank you. So my topic of today's discussion is geochemical signature from the Earth's mantle and how we find them. So let's start at the beginning. As we know, I think all of us know that the Earth has been accreted from the protoplanetary disk at about 4.6 billion years ago. So I have written 4.6 GA, which is a convention in geology, which means giga-annum or billion years ago. So the Earth has accreted from the protoplanetary disk. This is a schematic diagram taken from the internet, and it consists of the general material that consists of the solar system. And the composition of any of the planets depend on where it has been accreted in the solar system. As we know that the heavier material tends to stay near the sun, and the lighter, the volatile elements tends to go to the far back of the solar system. So this is to say that we have an idea of what the bulk Earth is composed of. So after the formation of the Earth, the first thing that happened is the formation of the core. The bulk Earth fractionated, as there are many heat generating elements and the radioactive elements inside the Earth, and because of their heat, the whole Earth started to melt and fractionate, and the core formed at about 30 million years after the accretion. And after that, the continental crust started to form. Now, there is an ambiguity of when the continental crust formed, but the general idea is that the continental crust started forming at about 4 billion years ago, and the bulk of the continental crust was formed at about 2.5 billion years ago. So I think you have seen some pictures like this. So this is the basic tectonic model of the Earth. That is the oceanic crust, which subducts usually around below the continental crust. It can also subduct below the oceanic crust. And there are various magma generating locations in the Earth. And in this picture, we can see some locations where basalts are generated. So for example, one is the arc, that is where the subducting plate is going down and magma is generated and comes out here. And another is the back arc, where in here, behind the arc. Another can be the continental rift, where the continent is spreading out and rifting, and there is basaltic magmatism. The most general type of magmatism is in the, which is called as MORB, which is the mid-oceanic ridge basalts. And another is oceanic islands, which are usually in the middle of the oceanic plate. And we can see some basaltic magmatism in this place. So as we can see from this picture, that we cannot find the mantle directly anywhere. So the mantle is closest to the within our reach, like the closest to us is at the mid-oceanic ridge. But there is a problem that there is a huge ocean above this mid-oceanic ridge. And in the continental crust is very thick, up to 100 kilometers, so we cannot usually reach the mantle through here. There has been many attempts to reach the mantle by drilling. So the first of which is the Mohole project in the 1960s, where the Americans tried to drill to the mantle on the oceanic crust from a floating platform. And the next was, this is also like the space race, the American versus the Russian race. So Russians tried to drill the continental crust on the land. And there has been many drilling projects. Another example is the Chikyu 2007. These two are the first ones. Later, there have been many. So they also tried to drill the oceanic crust and reached about 7,000 meters below the seafloor. These two reached about 1,000 to 1,500 meters. And the essence is that all of them failed to reach the mantle. So we cannot have any direct samples from the mantle. But we have some examples from the mantle rocks. One is the xenoliths, which we can get from the basaltic magmas, basaltic magma comes up from the mantle, carrying some fragments of mantle rocks, and we can study them. Another example is the ophiolites, which is that during subduction, some parts of the mantle and lower crust may be abducted on the ocean, on the continental crust. And later, the top part is eroded and we can access this part. So although neither of them is directly the mantle, but we have some idea of what the mantle rocks look like. So why do we study the mantle? You can ask. So one is that in the bulk earth, apart from the core, most of the earth is the mantle. The crust is very thin, and all of the elements, all of the components come from the mantle. So any volcanism, which is a very hazardous thing, that the sudden volcanisms may affect many people, many countries, and we have seen some recent volcanisms, and also volcanic related earthquakes are there. And in general, in order to know the history of the earth, how the processes in the earth occur, we need to study the mantle. So let's take a look at how we do it. So geochemistry is the study of the chemistry of earth. We study the elements and isotopes and how they behave in the earth's mantle, crust, and magmas. So one thing is to divide the elements in order of how they behave in the mantle and the crust. So there is the major elements. These 10 elements, in their usually in their oxide form, they are reported in their oxide forms, such as the silicon dioxide, MgO, Al2O3, DiO2, and so on. Another thing is trace elements. In general, there are anything else present in the rock, usually in ppm or ppb levels. Another thing that is very important in geochemistry are the isotopes of certain elements. So we will look at these later. If we look at the periodic table, we can see that any of the elements can be the trace elements, but most importantly are some of these, and especially this, lanthanides. So these are known as the rare earth elements. In the transition elements, usually, and the rare earth elements, usually the elements are divided in this format. So that is, this is a plot of ionic charge by ionic radius. So when we have some elements which show relatively low ionic charge, +1 or +2, and very high ionic radius, which comprise of potassium, rubidium, calcium, barium, lead, etc. And we have the high ionic charge versus low ionic radius, which are these. These are called the high field strength elements, and these are the large ion lithophile elements. So why do we do it like this? That is, when there is a melt or fluid present with along with some solid, that is the partial melt of the solid, usually these tend to go into the melt faster than these. To note that all of these are trace elements, none of these are major elements. So rubidium, barium, potassium, titanium, lead, these like to go into the melt. These like to stay in the solid. And incompatible elements, such as these, are very important in igneous geochemistry. This is a plot of the solar abundance of elements. And so we see a zigzag pattern like this because of the nuclear stability of the elements. So in order to eliminate, so this is a very difficult thing, right? Like we cannot compare one element to another because of this, their abundance varies a lot. So what we do to get rid of this, we normalize. We try to get a, so we get the composition of some certain rocks, such as the primitive mantle or the mid-oceanic average mid-oceanic ridge basalts, and normalize any rock, any elemental abundance of any rock to that particular value. So here is an example. This is how we do. This is a primitive mantle normalized diagram. So we get, we analyze some rock, we get the abundances of trace elements, and we divide that by the primitive mantle, and we make this type of plots. And this type of plots help us to understand the nature of the rock. And as we can see in this rock clearly, if you just take a glance at this rock and this data, you will see that this is a trend, this is a trend, this is another trend. So 3 are different. So looking at this type of diagram, we can say that where this rock comes from. Now we come to isotopes. Isotopes are very important in igneous geochemistry. So there are radioactive isotopes such as rubidium, samarium, uranium, etc. And they decay into various radiogenic daughters, their respective radiogenic daughters. And heavy isotopes are not fractionated in nature. So they are treated in radiogenic isotope geochemistry, such as lead, strontium, neodymium, hafnium, etc. And lighter isotopes are fractionated in nature. They are treated in stable isotope geochemistry, such as magnesium, iron, sulfur, carbon, oxygen, etc. So how do we do radiogenic isotope geochemistry? We get a rock from the field, we analyze its isotopic ratios. So why do we analyze ratios, not the absolute abundance? Because of the techniques used in isotope geochemistry, it is better to handle the ratios, such as that the radiogenic daughter divided by some stable isotope of that element. So for example, in this case, we can see the 143 neodymium divided by 144 neodymium. 144 neodymium is a non-radiogenic daughter of neodymium. Non-radiogenic isotope of neodymium. Similarly, in case of strontium, we divide 87 strontium divided by 86 strontium. 86 strontium is a stable non-radiogenic isotope. So then if we plot this type of diagrams, that is one versus the other, we can see that if we consider that there was some component in the mantle, and that component mixed with some other component, and those two components have different isotopic ratios, then when they come together, they will mix. And their mixing behavior can be plotted like this, that can be modeled in various ways, and they lie in a mixing line. So when we get our rocks from the field and analyze their isotopic ratios, we usually get some data, perhaps in here, and then we estimate and guess that what the end members might be. So that is the basic isotope geochemistry. And next, we will look at some examples of how we work and how geochemist works and what goes on in the lab. So, good thing about being a geologist is you can travel around and look at nice places like this, and many places you can go around. And we collect rocks from here. These are some road cuts. So when the road was made, these mountains were cut, and we can gather rocks from this part. This is a river cut, and we can gather rocks from here. And then we break the rocks, bring them to the lab. And this is a fragment of rock. This is a slide which we make by sticking a piece of rock to a glass and then thinning it out gradually to about 0.03 millimeters. And in case of geochemistry, what we do is we get this rock, clean it, that any soil or any weather part does not remain to it, and then grind it to a powder. And then we digest it using acids. Then we take it to the clean lab. So what is a clean lab? Let's take a peek at the geochemist lab. So it is a very closed room kept with very high pressure inside, relatively higher than the outside. Why is that? Because in order to stop any air from outside to go inside. How do we get air inside? So you can see in here, this is a air conditioner equipped with a HEPA filter, that is a very high purity filter, and the air comes in through the top for our case. And we maintain a higher pressure than outside. And so we don't get any contaminated air from outside in this lab. And these are clean benches, clean evaporators. These are even cleaner than the room. So let's see in the next slides. So this is how we look when we go into the lab, all wrapped up like this, clean roomware. I think you are used to seeing pictures like this because of the pandemic. And this is the clean evaporator. So the room is equipped with HEPA filter, which is high efficiency particulate air, which removes 99.99% of particles down to 0.3 micrometers in diameter from the air. And these clean benches are equipped with ULPA filters, which is the ultra low particulate air filter, which removes 99.9995% of the particles down to 1.2 micrometers. And this is the clean evaporators, where we evaporate our samples, dry our samples, and prepare the different, prepare the appropriate process for isotope geochemistry. And in the clean bench, we can see like this. This is a very clean environment, and these are some columns. We are preparing some samples. We are separating elements from the whole digested samples. How do we do that? So elemental separation is a very important thing for isotope geochemistry. First of all, we dissolve the rock powder with acid, and then we put it in an ion exchange resin column. So, and distribution coefficient of any element changes depending on the liquid and solid medium and concentration of the eluent. In most cases, this is an acid, and the appropriate eluent is chosen, and the solution is put through the ion exchange resin, and we discard some part of it and collect our target element. So we discard the other elements and collect the target element. And this is another part of our lab. This is the Milicu machine. This is the ultra pure water generating machine. And we also have to treat the waste very efficiently. We cannot throw it in the drain. There are particular, like we store it and then dispose of it according to the rules of the university. So after our sample is prepared, we use this kind of filaments and put it in a machine looking like this, where we measure the isotopic ratios of our rocks. So as you have seen that we spend a lot of time in a clean environment and cooped up in a lab. So there is an inside joke in the geology community, which is this, that geologists are people who like camping, and geochemists are here. Isotope geochemists are here, they're lab rats. Geophysicists are here, they're computer geeks. And there's a thermal barrier in between them. So the basic sense is that geochemists do not like geophysicists, and the geophysicists do not like geochemists. Although the situation is changing now, this is just a joke. So that's all. I will end my talk in this note.
Thank you, Bidisha. Thank you for that wonderful talk. So if there are any questions from the audience, please feel free to unmute yourself and you can ask the question. If not, we'll move on to our reviewers. First, Dr. Bandyopadhyay, if you could have your reviews.
Thank you. Thank you very much, Bidisha. It was a very nice talk from being from a different field altogether. I think I thoroughly enjoyed what you presented, and it was also, yeah, it showed, maybe the last slide was a summing up of what you do and where you are positioned on this ternary plot. I have some general comments and some specific comments as like the first time. For the first speaker, and maybe I would take as also we discussed before that it might be different ways of presenting the whole essence. Your title had a very nice attraction because it was something like, okay, how are we going to know something from the mantle? And as you progressed along the topic, I was trying to see how much are you revealing from the title of your presentation. And unfortunately, I felt that the storyline kept on changing a bit back and forth. So it was difficult to follow a very nice storyline all throughout. You presented very nice, interesting concepts, I would say, also how you work in the lab, how does your lab look like and what you are doing in there. But I was more trying to see how all those dots are connected to your title, and which was not the case. And when you came to the last slide, I felt like it's suddenly finished. So I was expecting more. I was feeling that you were almost in the middle of your presentation, and then it suddenly ended. And what I thought is that if I were you, I would have actually started probably with something humorous, as you made in the last slide, and try to go in slowly from that thermal barrier towards, if you are more towards the lab rats, kind of going to that area. Would have been very exciting because you covered very big scale, and then you came down to an area where you're working with chemicals and where you're trying to quantify isotope, and you're using a very high-end mass spec to do that. So I think the whole talk could have been arranged in a very different way. And one thing that you must think about is that, like the previous presenter had a very nice overview of what is coming next. It was very difficult to understand why are you saying the next topic. So it's all about structuring. It need not be a outline slide as the previous speaker, but also you could have used this plot coming back in the different parts and showing how you're moving, let's say from this, as we call this tie line in the center to your vertex point, right? Could have been one thing. So overall, the main point for that, what I wanted to mention is that your talk missed that the storyline, the connecting of the dots, that you had so many nice things you discussed, and could have been better if you had structured it. Another suggestion to do that could have been if you use some what we call as bumper slides, basically subdividing the parts, the whole presentation into parts, because then it's much easier to follow where you are in the talk. So that was kind of the main point. The second thing is that you did mention somewhere on slide number 6 or 7, why you actually want to get information from the mantle, and why people have started to drill in. And you mentioned a bit of the humor between the US and Russia, for example. And maybe this could have been something you could have made more stress on at the very beginning of the talk, because I felt that this was a really important motivation for you to work on this field and also present to us. But you kind of ran through that main point without any stress in a slide which was probably unrelated to that. You just kind of, it felt to me, you just remembered, I need to tell the audience now, why am I interested in the mantle? But for me, it felt like this could have been a starting point for the discussion. So that is another point I felt. Some of the slides could have been animated, I felt as well. Like, for example, slide number 8, where you discussed this periodic table and you said, okay, these are the elements which are of interest. It could have been nice because a periodic table is a bunch of different things and nice colors. So it was difficult to follow where you are wanting your audience to look at, because it's a digital presentation. And I think to keep audience attracted to such a nice piece of work, you need to kind of draw the attention, okay, this part. So you could have like faded off the rest of the periodic table and just focused on that part, or just a circle around, something like that. And another where you talked about, I think it was on slide 12, you said that there are some trends. And then you moved your laser pointer a bit over the graphs, and I didn't understand what trends you were referring to. Because again, you should remember there's a generalist audience who has interest for science and is trying to get as much science as possible out of curiosity, more than being specialist. So it would have been nice if you spent a bit more time in explaining, because it also seemed interesting. And final thing that I wanted to kind of highlight is the way you have presented and the way you have brought in the US, Russia, and this humor. I think you could have molded the whole presentation in that storyline, because you are a good presenter, in the sense that you were cracking jokes here and there and trying to connect. You also brought in the idea that wearing the space suits into a clean room is similar. We know it from the pandemic situation around. So there were these parts, and you are a presenter, it seems, although this is the first time we are hearing you. in this forum, but it seems like you like to connect it to experiences that people have, which is a good thing to do. But those experiences fell out because they were not following a gradual progression of your storyline. So use humor. That's very nice when it's not hitting the audience too much. But in principle, it is better to keep on connected to your the main message that you want to share. So with that, I think I would like to thank you for opening more curiosity in this field and also showing how geochemists work at kind of the boundary of something very big and breaking rocks and visiting nice places, collecting rocks, and then doing some high-end mass spectrometry to know what is going on. Thank you.
Thank you, Dr. Banerjee. Moving on to our second reviewer on the panel, Dr. Sinha.
Yeah, hi. So first of all, Bidisha, very nice talk. Your talk reminded me of this article in National Geographic I read when I was a kid. So this was an issue, dating from sometime in the 1960s, and it was on Project Mohole. And essentially the article was saying that, Jules Verne's Journey to the Center of Earth is about to become a reality. So, reading that, I thought, it's only a matter of, maybe a few years before we actually get to, the center of the Earth, so to say. And then, somehow I lost touch with that excitement, and it was, fantastic to come back again after, quite a few decades and see, the story is, still kind of unfolding, but no closure has been reached as yet. So that was great, connecting it with, that big adventure of the 1960s. Now, everybody has their own style of giving talks, and as Sulalit has already pointed out, you actually have a wonderful presentation style. And there were indeed flashes of brilliance in your talk. But you know what, just to reiterate Sulalit, it was like, somehow those, brilliant parts didn't actually mesh together to form an incredible whole. So there were, I could get each of these parts, but somehow at the end of your talk, I'm, left asking, what is the take-home message? What am I supposed to, remember or recall? So if my wife asks me, during dinner, so how did you spend your evening? I'm going to be left searching for, okay, how do I actually summarize your talk? I could certainly tell her about, like there were these cool pictures from your lab, all this, spacesuit-like things, clean rooms and so on. But what was your talk about? I'm still left, scratching my head. How am I going to summarize in, let's say, 2 minutes and tell my wife that this is what your talk was about? Right? And so maybe that's what you should first ask yourself, that, what is my audience supposed to, let's say, tell their family members after they've listened to my talk that, this is what the talk was about, okay? That this is the main storyline, okay? It's very nice to have, very interesting parts, as Sulalit already pointed out, this whole Cold War struggle between US and Russia. See, I knew about Mohole, but I didn't know that the Russians also had a similar thing going. So, that's an incredible story there. As Sulalit already pointed out, you could have also mentioned a bit about it. And I'm sure that would have been very exciting to your audience, that, how the arena of Cold War not only was on the surface of the Earth, but also was, like, so to say, digging deep into the Earth, right? Now, very, what do you call it? Wise man once told me that you should never structure your talk like Columbus. So, the story about Columbus is that he started out not knowing where he is going. He reached a place not knowing where he is, and he came back home not knowing where he has been. Okay? So in a sense, after, going along with you on this journey, I'm left feeling like Columbus. So just try to make sure that doesn't happen. I saw incredible sights along the way, but, I'm still left feeling confused. Okay, so uh, you know, you of course mentioned that why we study the mantle, but that's a very general kind of statement. I'm still not sure what is it that your research kind of sheds light on as regards the study of the earth. How does it fit into the broad story? I understand that you do geochemistry. I understand you gave the details. So I understand that you are going to the field. You're coming to the lab. You are using let's say the thermal ionization mass spectrometer. But I'm still kind of as you said, left curious as to what is it that you do? What is it that you found that tells me something about, let's say, how the earth formed? You mentioned, the importance of trace element signature, that you could, that tells you where each of these rocks come from. But I'm still not sure whether that's all that you do. I mean, are you just analyzing rocks to, find out where they're from? But in that case, why is it of interest? Why is it, what does it tell you about how the earth formed? You had all the slides about isotopes, radiogenic isotope geochemistry. You had curves showing, like this neodymium and strontium. But again, they didn't actually fit into a coherent whole. So your last slide was fantastic. In fact, I would like to know the source of your image, whether that's something that you created or that's something from your lab, because I just want to steal that picture and hijack it for my own purposes. Okay, fantastic picture. But as Sulalit said, again, it could have fit in some other part of the story in order to motivate the thing, because in a sense, it kind of ended the story, but as Shulit already pointed out, in a very abrupt manner. Maybe it's appropriate place for somewhere else. Okay? Basically, when we are talking about your journey as a chemist from the field to the lab. So overall, I think there's great promise. You definitely are a great communicator. You have the right eye for visuals. You have the right eye for, and you have the right ear for anecdotes. All the ingredients are there. You just need to, put it in the right order to make this, extremely memorable talk. Okay, but I'd still like to congratulate you for great work.
Thank you so much, both of you. Both, I would like to thank both of the reviewers for their so nice comments.
Thank you everyone for being present, and have a good day. Thanks.